me trying to explain recessive genetics to my mother after dinner one night because I'm a really stable person.
Well, on the way there.
Oh yeah, no, I take tons of notes, and then because I use rocket books for taking notes, I scan the pages and then erase them.
How easy is it?
You just take
It's all good. We'll figure it out. Could be, yeah. Could be. If there's a problem, then I'm sure we can figure it out. When I get back with you. We'll be all good. Okie dokie. All right. So,
Here's an example of a note that
we're back for day number 2 here, right? So we're slowly ticking away at the amount of classes that I have with you guys, for better or for worse, right? You still finishing our answers? You didn't know it was due today? Is that what you said?
No. I just realized when I was about to do
But the answers were all wrong. Oh no.
my room, just missing.
I see. That's a good way of putting it.
the missing was there.
I didn't lose points, they're just missing, right? So, okay. Anyway, so a couple of things. Tomorrow, right, we start our labs, right? So I think tomorrow, and then there's also a section on Friday, right? Is that what it is too? I think? Yeah. So a couple of you guys have lab tomorrow, and then some of you guys have lab on Friday there too. So don't forget that you guys are going to be bringing your pre-labs with that too, right? And don't forget to come with your lab coats and goggles and attire and all that other kind of stuff there along with that also, right? So pre-labs, watch through those videos there so you guys have a little bit of an idea about, you know, what a SEP funnel is and some of the uses of it, I suppose. And then take a look at, I think recrystallization is going to be very important this semester. So definitely watch through that video and we'll get quite a bit of practice with that as we go through, right? But always coming in with a good idea of what we're going to be doing is going to help you guys get through the lab there a little bit quicker because most of you guys are going to be working on your own for the labs, right? So you're going to have to rely on only yourself, okay? The worst boss to have, right? Yourself. So we'll have to see, or we'll have to make sure that we're prepared for what we see in there. What's up?
Do you want us to print out the pre-lab so we turn it in online and then we print it out and bring it to?
No, there's nothing to turn in online. Right? You guys just write it out and bring it in. So,
Okay.
Yep. You guys will be needing that stuff while you're doing the lab, right? That kind of thing. So, okay. Let's see. So we took. Yeah. What's up?
About the pre-lab, do you want us to handwrite it or it's typed up okay?
Whatever you want to do. I mean, either way's fine. Like I'm not going to be that picky about it. Like if it were me, I handwrite that stuff. So, because you're going to be turning it in for as part of the, you know, the post-lab stuff also. So your pre-lab plus your post-lab is basically the grade that you get for the lab is what it is. But we'll talk about that a little bit more too as we kind of walk through the things. Okay, I think that's all I have to say in terms of that kind of stuff. Yeah, I don't think there's much else. Okay, so let's get started with prayer and then we can continue on here. But Lord, we just thank you for another day. We just thank you for another opportunity that we can come here. We can just learn a little bit about the creation that you made, Lord, and just how the world works and how you put it together, Lord. Just help us to keep our eyes on you and the things that you would be explaining to us, Lord. Just open our minds and our hearts to the things that you would be saying to us today, Lord, and just help us to reflect that to others around us in whatever way that might be. Just give us the courage to speak up when you want us to speak up, and also give us the courage just to stay quiet when it is that we should stay quiet, Lord. We pray that we just hear your voice today and follow the path that you've laid out before us. We just ask all this in your name. Amen. All right. So last time we talked a lot about things that you guys forgot. Did you remember that?
Mm-hmm.
Yeah. Okay. Good. So, so we remember a little bit about all that kind of stuff. But we need to go back and fix some issues, is what it is, right? Okay. What's the most important thing in organic chemistry? Something negative goes to something positive. Okay, what's the only negative thing in the universe?
Electrons.
Electrons, got it? So when I'm saying that something negative goes to something positive, what are we talking about? The movement of electrons, got it? Okay, now this is a key thing. Now you guys are writing this down and you guys are listening to me and it's in the book and it's even italicized in the book and all this other kind of stuff. And then I'm going to give you an exam, and you guys are going to be like, no, I'm not going to do that. I'm going to do something else. This is the key part. It's electrons that are moving. Because what does chemistry?
Electrons do.
For the most part, 99% of the time it's electrons, right? Unless we're dealing with nuclear chemistry, which we don't really deal with here. And even there, some cases, electrons are involved, okay? So we're going to be doing the movement of electrons. Electrons make bonds. Electrons are involved in breaking bonds. They're involved in being negative and going to something positive and all this kind of stuff, okay? So guess what it's important to recognize?
Where the electrons
Where the electrons are, got it? Because if we're talking about something negative going to something positive, that implies that they have to begin somewhere, right? And they have to end up somewhere. Does that make sense? So we have to know where the electrons are to begin with, we have to know where they end up. We have to know how negative they are, and we have to know where something positive is. What's the only positive thing in the universe? Protons, okay? Now let's think about this for just a second. Are we dealing with protons getting added or subtracted? No. So really, when we're dealing with things that are positive, what are we dealing with?
Electrons.
Electrons being taken away.
The absence of electrons, got it? Right? Because remember, protons are not really going to go anywhere for us. A carbon's going to be a carbon. It's defined by the number of protons that it has, right? Those aren't going to be moving. But we can have a carbon that's positive, and we can have a carbon that's negative, and we can have a carbon that's neutral. Got it? And that's all based off of just where the electrons are and where they end up and where they begin. You guys with me on that? They get the point across? Electrons, good, important, need to know, right? So now we're going to spend the next, 20 chapters talking about where electrons are, okay? Yay. But all joking aside, right, this is really all that we are going to spend our time with. Now, obviously there's complexities involved with this, okay? Otherwise we wouldn't have to spend all this time dealing with organic chemistry and writing all these different books and doing all this stuff that we do, okay? So for the first chapter, I'm basically going to go back and knock the rust off of the Gen Chem for you guys, okay? And then we're going to talk a little bit about how we draw molecules in organic chemistry, and that's going to be one of these key things, okay? For better or for worse, depending on, let's say, your own personal preferences. This room drives me nuts. I always like to pace around. It's like, here's 3 steps. Too small, man. And I can't even move my way back there and loom over you guys to make you nervous. And, jeez. Anyway, but for better or for worse, organic chemistry is a visual science, okay? Do you guys catch what I mean with this? Right, if you think back on your time in Gen Chem, how many things did we draw necessarily?
A lot of Lewis structures.
Well, a lot of times when you were bored, you were doodling things in the corner, right? So there's some flowers and some mountains, right? Right? You drew a lot of Lewis structures, but that was basically for what? Maybe 1.5 chapters, right? Aside from that, it was basically math-based, right? So not too much drawing. So organic chemistry kind of swings the pendulum in the other direction there. It's pretty much exclusively about drawing things. Do you catch what I mean with this? So if we're going to start solving a problem, we're going to need to start by drawing out the proper thing, okay? And then we're going to have to find where the negatives and the positives are, right? And we just kind of work our way down our line here of the tools that we will be learning to assess how a reaction happens in organic chemistry, or how to assess the properties of a molecules or things like that. So we're going to have to learn, and we're going to have to draw a lot of Lewis structures. Now, some of you guys, when you were going through the quiz here, maybe it took you guys a long time to draw through the Lewis structures. Right? Well, okay, we haven't done it in a while, but I promise by the end of maybe halfway through the semester, you guys don't even have to think about it too much. Sound good? No, because when you don't think about something, guess what happens?
You make mistakes.
You make mistakes. Got it? So I'm going ahead and telling you guys where you're going to miss points here too. Okay? Just like I told you guys, you're going to miss points with the whole negative and positive, and you guys are going to switch that around. I'm telling you, you guys are going to get just so comfortable drawing Lewis structures, you're going to forget what they mean, forget the information that they tell us. So you're going to have to always pay attention to what you're drawing with your Lewis structures there. Yeah, what's up?
So
question.
Yep.
Do we throw the lone pairs on those structures?
Yeah, we'll talk about that. Yeah. Okay, good. All right. So we talked about this a little bit here. So we talked about, let's say, oops, let me get it. Let's say today's an orange kind of day, right? How to build an atom. Right, to bake an atom cake, you need 3 parts. You need protons, electrons, and neutrons. Okay? Now I can tell from your stunned silence by this revelation that you guys had not expected this. Wow. 3 things to make an atom, that's nuts, right? Okay, so now the point being, okay, for those of you guys who haven't had me for a class before, and even if you had me for something like Gen Chem, what I'm going to get you guys to do in this class, or what I'm going to try and get you guys to do, is to think about things. Dr. H, I think about plenty of things, okay? All day long, I think about, you know, whatever, right? How to make muffins, or, you know, what I'm going to be doing later on tonight, or what do I have to do at work later, right? This kind of stuff. But the point is kind of in the context of this class, I need you guys to think about what you know about all the information that you guys have stored up in here over your years of chemistry training, right? You guys catch what I mean with this? So the last question on the quiz, what did I ask you guys? I said, hey, we've got a reaction in its second order. I said, elaborate on what this means. Okay? Some of you guys wrote 2 sentences. I don't know, I didn't read, I'm using my magic professor powers here to guess. Okay? Some of you guys wrote 2 sentences about what that means. Some of you guys probably wrote me a whole paragraph that I'm not going to read. I'm not saying it's wrong, I just don't want to read that. Sorry, I told you guys, I'm not lazy, right? What am I?
Caloric efficient.
Time efficient, thank you, okay? So if you're writing your resume, put your time efficient on there, right? It's very good, okay? So, but what's the point of that question? I just asked you a simple question about second-rate kinetics, right? What do you guys remember about it? What information can you get out of what the information I give you, right? So I need you guys to start thinking a little bit deeply about things, what I'm trying to get you guys to point at. Critical thinking, this reasoning that we talked about last time, right? So I know you guys know how to build an atom. That's not the point. Now the information that we just talked about is how important electrons are to everything that we're going to be doing in organic chemistry. So when I tell you about electrons and protons and all these kind of things, right, it's not just the context of, yes, I know how to bake the atom cake. It's also what are the important things that I need to pay attention to. You with me on that? Are we going to deal with neutrons too much in this class? Yes.
What?
But more in the lab side of things, okay? So if you guys were reading through the pre-labs and kind of watching some of these things, it was talking about NMR, or nuclear magnetic resonance, okay? That's solely based on, well, yeah, I guess that's a fair statement. It's solely based off of how many neutrons there are inside of an atom itself, okay? And so when we get to that part, we will talk a little bit more about where neutrons are important with that. In the context of things that we're going to be discussing in class, we're not going to deal with that too much though, okay? So like I said, that's more nuclear chemistry, and we deal with that with nuclear magnetic resonance, got it? So protons, electrons, neutrons, you guys got that. So I can build an atom. What defines an element?
The number of protons and electrons.
There we go. So right, we have elements, right? Defined by protons. Cool. Got that. That's kind of self-explanatory. How many elements exist naturally?
A lot.
Specifically.
120 something.
So there's 90 naturally occurring elements. Okay. Basically starting from hydrogen all the way up to uranium. For those of you guys who are quick on this, who have your periodic table in front of you, uranium's element number 92. So how did I get 90 from 92? Well, there's 2 along the way that aren't naturally occurring, okay? So, now what does that matter for you? Do I expect you guys to memorize 90 naturally occurring elements for the exam? No, of course not, right? But we are going to be dealing with organic chemistry, so there's one element in particular that we're going to be dealing with.
Carbon.
Carbon, got it? So all of organic chemistry broadly defined is the reactivity and the chemistry of carbon itself. Got it? So if there's somebody asking what's the definition of organic chemistry, we would say something along the lines of the chemistry and the reactivity of carbon and the transformations it can undertake, things like that. So out of all those 90 naturally occurring elements, we're really going to be zooming in on that one, okay? Doesn't mean we're only going to be dealing with carbon here. No, of course not. Carbon's going to have its best friend, okay?
Hydrogen? Hydrogen?
Yeah, hydrogen's going to be carbon's very, very good friend. And so we're going to be dealing with hydrogen quite a bit too. We're also going to be dealing with oxygen a lot. We're going to be dealing with the halogens a lot. We're going to be dealing with our alkaline metals quite a bit. And we're going to even see our alkaline earth metals quite a bit. We're going to see some transition metals here and there. Okay, so I just named everything on the
You didn't name the
periodic
actinides.
table, right?
You didn't name the actinide series.
Okay, no, we're not going to be dealing with those. Force and unforced. You had a question?
Yeah, I was just gonna ask, what are the two that aren't naturally occurring?
Technetium and what's the other one that I'm forgetting at the moment?
Now he's gonna put this on an exam.
No. Technetium and what's the other one that's not naturally occurring? Beryllium, I think maybe is not natural. I forget. I know technetium for one of them. I have to double check on the other one there. Good question.
I think so, probably.
Do you guys know what technetium's used for? You guys ever went and had like some imaging done? Right?
Digital
I remember one
X-ray?
time I had to go do this and they give you a technetium milkshake. Right? Like it tastes like grapes. No, it doesn't. It tastes like grapes that's mixed with chalk. And then you have to drink it and it's used as a contrasting agent, right? So colloidal technetium is what they use sometimes for imaging as a contrasting agent here. So don't believe the lies, it doesn't taste good. So
Where's technetium?
it's in the transition metals, it is right there. Yeah. Anyway, so we're going to be dealing with carbon and oxygen and the halogens and your group 1A metals, your group 2A metals, a little bit of your transition metals. So what am I trying to point you guys at?
Everything?
Everything on the
Periodic.
periodic table, got it? So step, maybe we're on step 3 or whatever at this point is, understanding what the, how the periodic table is arranged and the information that we're given, or excuse me, the information that we can gather out of the periodic table itself, right? So all the elements are arranged on the periodic table. Again, I don't think I've given you guys information that you haven't heard at some point here, right? Behold, a table. Okay? Wow. I'm impressed. Looks like somebody spent a lot of time putting this together. Good? You guys know everything about this?
No.
No? Okay. What do we know about this? Yep.
How to identify trends?
Okay, what do you mean by that?
We know, like, from last year, we know how to identify the major groups, like the halogens, what are their major characteristics, same with
Okay.
noble gases, and how to, like, predict, what's gonna be more electronegative. what's
So
gonna-
let's pause for just a second, right? So one important thing to recognize are the different, let's say, families in the periodic table, okay? Now what do we mean by families typically? Hmm? I don't know who said something like
Sorry, they react in similar ways.
Okay, so they're gonna have similar properties, so hang on to that thought, but what do we mean by family though, if we're looking at the actual structure of the periodic table?
Isn't it ones that have the same number of valence electrons?
Okay, so they're in the same family, we're typically talking about the up and down, the columns there, right? So Rachel mentioned the halogens, right? So fluorine, chlorine, bromine, iodine, acetine, those right there, right? Those are in the same family, okay? Why are they in the same family? Well, I've got an older brother, okay? He's 2 years older than I am. Guess what his job is? He's a chemist, okay? I'm an inorganic chemist by training. Guess what he is? An inorganic chemist by training too, okay? You guys get the point? We're both big dorks is what I'm saying, right? We're all in the same family here. So much like you and probably some of your siblings, if you have them, right, you probably share a lot of interests with them too, okay? So it's kind of the same idea here when we're talking about family. They're going to behave in similar ways, okay? Doesn't mean they're always going to behave in the same way. No, okay? Of course not. They're not the exact same thing, but in general they share similar trends of things, okay? So it's important to recognize that this is one of these key things that I know I've emphasized with you guys, and I know you have it here, but we need to think about applying this. What do I mean by all this? They're going to behave in similar ways. Now look, here's the truth, okay? I'm going to rip you guys off for your tuition money. Oh good, you guys aren't mad. All right, yeah, whatever. I am not going to teach you all of organic chemistry. In fact, I'm only going to teach you, okay? Very, very small amount of it. And you guys still aren't mad about it. You're like, yeah, that sounds good too.
We're resigned to the fact that the education is an excellent.
But here's the thing that I am going to teach you guys about. We're going to spend a lot of time talking about the chemistry of how oxygen and carbon relate, okay? And how they react and how they change and how we can do different things. We can oxidize and reduce it and all that kind of stuff. Are we going to spend a lot of time talking about sulfur? Not as much as oxygen, but how do you think sulfur is going to react with carbon? In a very similar way. You guys got it? This is important. Is it going to be exactly the same? No. Could we predict what sulfur might do under similar conditions? Absolutely, and that's the whole point with this, okay? What's up?
Isn't sulfur that really annoying one that like absolutely refuses to even pretend to behave to like do the octet rule and just like you don't know how many electrons it's gonna be sitting there with because it'll just have as many as it wants type thing?
No.
I just seem to recall it like being attached to like an absurd number of hydrogens and some.
An absurd number.
Yeah.
So we'll talk. So hang on to that thought, though. We'll come back and address the octet rule in this a little bit. Okay. But you guys get what I'm saying with families? This is my favorite way to ask you guys exam questions.
You need a cough drop?
Yeah. I'm giving you guys subtle hints, okay? My favorite way to ask an exam question is, hey, did you memorize what we talked about in class, or do you understand the concepts that we talked about in class? If oxygen does this, do you think sulfur would do the same thing? Why or why not? Got it? This is why it's very easy for me to write exam questions for organic chemistry. I can just change one thing and then expect you guys to know how to answer that, even if we didn't explicitly talk about it in class. Oh, God, can't get this. Unbelievable. You guys get the point I'm making though? I promise, all joking aside, I will never ask you guys a question on an exam that we didn't discuss the concepts about in class, okay? I don't need to be a jerk, okay? I'm not going to go looking for difficult things to ask you guys about. But I do like to know that you guys are understanding what we're following along. And that's the difficult part about this class. If you just try and approach this with memorization, well, I'm not saying you can't pass the class, okay? But I've never had a student come through here who could memorize everything and get an A. I'm just letting you guys know. Okay, you have to understand, you have to process, you have to apply the information to this class. Got it? So start to ask yourself everyone's favorite question as a 3-year-old. Why? Okay? Always 5 good questions you can ask. Who, what, when, where, and why, right? And those are all important questions to ask here in organic chemistry. Yep. Yeah, that might be useful. But it's okay, 5.5 good questions. Thank you. right? You guys with me on this though? So paying attention to families in the periodic table, very important trend, okay? So we have our halogens that are, I'm just gonna kind of quickly bracket them off here, right? So we have our halogens. We're really not gonna deal with astatine here at the bottom, okay? We're gonna spend a lot of time with chlorine, bromine, and iodine. Fluorine is kind of its own little beast, okay? We'll talk a little bit about it, but way more in the second half of this, or excuse me, the second semester of this class. Okay? Yeah, what's up?
What's the UUS? Is it also a halogen or is it?
Yeah, I forget what they actually did give it a name recently.
Tennessine.
What is it? Is it Tennessine? Yeah, okay, so it's just one of those elements that exist for fractions of a second that they made, in a big expensive machine, and then they get to name it after, certain things, so.
Does it behave like a halogen?
We have no idea, honestly, right? We suspect that it does, but I don't know what the half-life of this is, but it's probably like fractions of a second, so how can you really study that? So it's more the realm of a little bit of physics or theoretical chemistry. But orange is our halogens over here. So lithium, sodium, potassium, rubidium, cesium. Those are our group 1A metals. Yeah, what's up?
Why do like the really large elements down at the bottom exist for such a short time? Why is it so difficult for them to exist stably?
Why is it difficult for them to exist stably? There is a certain, let's say, what's the word I'm looking for here? A sink of stability when it comes to nuclei. So iron is the most, iron is the most stable nuclei. So when you're looking at radioactive decay from even something like uranium and things like that, they all tend to go all the way down to iron is what it is. So everything above iron kind of goes back to iron, and everything below iron can get fused up to iron is what it is. So we think of these nuclei as just this, kind of unchanging mass, just because we don't talk about nuclear chemistry all that much, right? But just like we have, let's say, stability of different compounds, the same thing can be applied to the nucleus itself. So there's some combination of the weak nuclear force. If you try and jam, let's say, 115 protons together, right? That's a lot of things to kind of keep together in there is what it is too. And so we'll just try and break apart the smaller ones is what it is. Okay? Have you thought about that? Protons are all in the nucleus. What happens when you put a positive next to a positive?
They rip it up.
How come a nucleus stays together? Right?
Well, how does it?
Yeah. What's attracted to positives? How come the electrons don't go flying into the nucleus?
Because of the strong magnetic force of the nucleus.
Negatives and positives attract. Why do you even exist? All laws of nature say, right? I'm serious, right? All laws of nature say that negatives and positives come together. If all the nuclei smacked into, if all the electrons smacked into the nuclei, guess what would happen? Right? And you wouldn't have to take the first exam. So there's positives behind all this, all I'm saying. Yeah, what's up? What's up?
Does it have something to do with quarks, like how the protons stick together?
That's a good question for Professor Sadowski. Right? So I think his background is in theoretical physics, right? So that'd be directly up his alley there. Anyway, so in green we have our alkaline metals. Everyone's favorite metals. Why?
They're easy to bond.
That's going to be important for us. But everyone loves sodium, right? Because we've seen the demos with throwing it into water, make big fire, things go boom, everyone happy, right?
Mm-hmm.
So,
Eighth grade, very happy.
All right, so sodium, potassium, we're going to be spending a lot of time with those, lithium there in particular. For our purposes, right, and what you guys learned in Gen Chem, it's very true here too. We pretty much will always see our group 1 metals there in a +1 oxidation state, right? Now, one of the rules of life is that it behaves like the force, right? And what do we know about the force? There always has to be a
Good sign and bad sign.
good sign and bad sign, otherwise known as the
Dark side.
balance, right? The light and the dark, the yin and the yang, right? You guys with me on this? So if I have a positive sodium around, guess what I have to have somewhere? A negative something. You guys with me on this? Now this is going to be important because we're going to be lazy. Except we don't want to call ourselves lazy, so we're going to be
Time efficient.
time efficient. Got it? And we'll talk about what we mean by time efficiency when we get there. But we are going to be dealing a lot with charges as we go through this class. Okay? Especially when we get to intermediates, where charges get formed and converted pretty quickly. But remember, there always has to be a balance to these things. Got it? Now, we learned about this in Gen Chem, right?
Mm-hmm.
Okay, you nodded. How did we learn about it? I was just agreeing. Remember what we called ions that exist on both sides of the equation? That we can just cancel out when we're balancing things?
Oh,
Spectator.
Spectator ions, got it? Right, so they're not directly involved in the reaction, but they're there to balance charges and things. You guys with me on this? So we learned about this stuff, okay? So we're going to be dealing with spectator ions, and most of the time it's going to be one of our group 1 metals there that are spectator ions. Sodium, lithium, potassium, these kind of things. You guys with me on that?
mm-hmm.
Cool. Okay. Right next to them, you got beryllium, magnesium, calcium, strontium, barium. These
We
guys
don't
here.
really see beryllium too much, do we?
You do in certain applications.
Like,
I think that's the one that's used in X-ray transparent windows, I believe. I'm pretty sure that's what it is. I could be wrong with that, but I'm pretty sure that beryllium is used for that. What?
wouldn't all windows be X-ray transparent?
No. Mm-mm. Depending on what you have in them, it'll absorb X-rays.
Like lead?
And among other things too, yeah. But anyway, so our group 2A metals are our alkaline earth. What do we know about those?
They're twice as positive as the...
2 of them are vitamins that we need for our bodies, magnesium and calcium.
Okay. It'd be minerals, okay. But you're right, they're very important for us. Okay. What do you mean by, Rachel, what do you mean by twice as positive?
I mean, they have a +2 charge instead of a +1 charge.
Why? Hmm?
They're missing 2 electrons.
No, they're neutral.
They can easily lose 2 electrons.
Aha.
Because
Okay.
they seek to...
So when they're in a compound, right? When they're mixed with something else, when they're there for the balance, they have a +2 charge. Right? So just like the first question on the quiz, or what I asked you guys about, predict the ionic charge for something. Got it? So be careful, right? Ionic versus elemental forms, these kind of things. How do we know that it's going to have a +2 charge? Yeah?
Because all elements are pretty much going to seek to have, to match up with the noble gases in their electron count, like their valence. I can't explain it well, but I do understand it, I promise. I just don't, I can't word.
What's up?
All the elements want 8 valence electrons.
All the elements want 8 valence electrons. Okay? So that implies that there's something called a valence electron, right? So what in the world is a valence electron? So hang on to that thought for just a second. We'll come back to that in just a minute, okay? So you guys are right. Okay, you guys are walking around the correct answer here for some of these things, okay? So hang on to those thoughts about valence electrons, that kind of stuff. But there's our group 2A metals, our alkaline earth, okay? We're going to be dealing probably the most with magnesium in this class. We're going to get into everybody's favorite reaction in the second semester of organic chemistry. You guys love using magnesium. For some reason, it happens every time. But anyway, we'll talk about that when we get there. We'll talk about Grignards and these kind of things, okay? In the middle here, we have our transition metals. This is, as I mentioned briefly before, this is kind of where I did my work on as a, in graduate school. I'm not an organic chemist by training, I'm an inorganic chemist. And we kind of deal with the chemistry of the stuff that's in the middle of the periodic table there. Guess what they do? Everything. They're the best. That's why I studied it, right? Yes, thank you. Okay. Go ahead. Feed my ego, please. Right? Now, transition metals, unfortunately or fortunately, are extremely important in organic chemistry. But we're not really going to talk about them too much in terms of how they work. Okay? Because what's organic chemistry? Well, it's the chemistry of how carbon gets transformed, right? So, inorganic chemistry is going to come back and tell you, okay, all those times we use transition metals to do some kind of change with carbon, here's how it worked behind the scenes. Okay, so it's a different class that's going to kind of cover those. Okay?
Are we gonna get to take that class?
Maybe. I'll tell you, and I can answer that question a little bit later. Why? Okay. So there's our transition metals. We're going to be seeing zinc and copper quite a bit. Palladium and platinum, we're going to be using those quite a bit. Ruthenium pops its head up here and there, these kind of things. So we're going to be kind of picking and choosing certain parts of the transition metals to talk about there. Let's see here. Let's go with, we'll do this. So there's our Tetris shape here almost, right? So for most of the time, we're going to be dealing with those 7 elements there, okay? The vast majority of the time, the vast majority of the reactions that we're going to be dealing with are going to involve those 7 elements, okay? Of course, carbon, you got that, okay? Nitrogen, we're going to talk about that quite a bit too. Oxygen. Our halogens are going to be extremely important functional groups for us. Okay, and we'll talk about what functional groups are in just a little bit. In addition to that, somebody mentioned it before, we got our buddy all the way up here, hydrogen. Okay, now hydrogen and carbon are going to be best friends. Usually where you see a carbon, you're going to see a hydrogen too. Okay? We'll talk about the implications of that. Now you guys in your Gen Chem talked quite a bit about hydrogen already. Okay? So you guys talked about acids and bases. Yes. Yes. So you guys remember all about that.
Every single thing.
Thank you. That's the right answer. Good. Now I don't have to cover it. We can watch movies on that day right there. All right. What's up?
Is there a name for that Tetris shape?
No, that's just arbitrary.
Okay.
Yeah. That's just me saying, hey, we're going to spend most of our time here. That's not like a family or anything for us to look at. Yeah. I think, if I remember my naming correctly, the carbon family is the tetril family, then the nitrogen's nicogen, and then these are chalcogens or something. I forget. There's some weird names for those things that actually is important, but not until you guys get onto graduate school for chemistry, right? So, which all of you guys, is that what you guys want to do?
Yep.
Good answer. Right. Anyway, so that's kind of the basics of how the periodic tables kind of fit together there in terms of different families. Okay, so who cares, right? Now I've got a lot of trivia knowledge. I can name things. I can look at things, but that's not going to give us all that much information. What's important to recognize about the periodic table, though? What are some things that we've learned?
It's cool.
Mm-hmm. Yeah,
There's a few fun songs about it.
there's a few fun songs about it.
The most electronegative metals are always going to, or elements are always going to be on the right-hand side of the table.
Okay, so we're getting to this idea of electronegativity. All right, so what in the world is electronegativity?
It's an element.
All of you guys fight about it. I'll turn around. Okay.
It's an element's tendency to gain or lose electrons, or how attracted they are to electrons.
Okay, so we're dealing with an element and how easily it can attract electrons. Okay, what's up?
Isn't it like how badly it wants to fill its valence shell, and how easily it can fill its valence shell? If you have an oxygen and a fluorine, the electrons are going towards the fluorine because it more easily will gain a electron valence shell.
Okay, so now we've kind of expanded our thoughts a little bit to include things called shells and how these shells are attractive to electrons. What else?
We've been saying how likely they are, or something like. I would say how good an atom is at attracting electrons.
Does it have to do with their orbitals?
So we have shells, right? Oops, shells, we have orbitals. We can attract things. Oops. Attract electrons. What else?
What about lowest energy state?
Okay, so we have something to deal with low energy. That sounds like 8 a.m.
Amen.
Forming anions.
Okay, so we have something about forming anions,
Bonds,
baby bonds. Okay.
James bond.
No, atom bombs.
That's a lot of stuff. Is that all true? Is that all correct? Andy, what's the textbook say? Should be there in the first couple pages. Or if somebody has their textbook open. The reading according to the Gospel of
Klein.
what is it in the back of?
Electronegativity is a measure of the ability of an atom to attract electrons.
Okay.
There's
What page are you reading off of it?
1.5, it's page 29.
Page 29, all right.
Or, I don't know, 9, I don't know.
Or 9?
9, my bad.
Do I have to go over numbers now? I'm just kidding.
I don't know how it is on your book.
Okay, that's fair. It's probably also in the index in the back there. There's probably a couple of definitions in there. So one more time for us, real loud. What is it?
Electronegativity is a measure of the ability of an atom to attract electrons.
You guys like that definition?
Very much.
It's very simplistic.
There's a couple of things, right? There's a couple of issues with that definition. The ability of an element to attract electrons. Is it just gonna what? Okay, I have an element here, is it gonna attract electrons from Canada?
Yes.
The answer is yes. Ugh. Okay. Do you think it's gonna have a good attraction to the stuff that's in Canada? No. Okay. So if I'm implying that I'm attracting something, okay, it's the reason why you probably chose to sit next to the person that you did. Maybe you're trying to be sly about it and get their attention. Like, oh, I don't understand this. Can you help later? And bat your eyes at them. Right? If you want to attract something, it implies that you have to be what? Close to it. Got it? The closer you are to something, the more it's attracted to you, right? So not only am I giving you guys organic chemistry tips, it's also
Dating
social and dating advice. Okay? So, right? What's up?
So would another way to be to look at it be like how close the nuclei of atoms can get to others? Because like with fluorine, not only is it one of the smallest in terms of radius, but doesn't that also mean that like because of that its nucleus can get a lot closer to the nucleus of what it's bonding to because of how small and electronegative it is?
So hang on to that thought there, okay? We're going to come back and we'll address it in just a quick second, okay? Some important thoughts in there, but I want to finish this and then we can get to that, okay? So we're talking about attracting electrons. Where do electrons live?
Outside the nucleus.
Okay, outside the nucleus in orbitals. Got it? So you guys mentioned something about orbitals there, yes? Okay, so if we're dealing with electronegativity, we're talking about how an element can attract electrons, or I think it said an atom can attract electrons. I like that definition better than element. Okay? How an atom can attract electrons, and electrons live in orbitals. So what do we need to know? What in the world an orbital is. Got it? All right. So, oops, that's my Gen Chem notes. You guys might want that better, but okay. Let me change it real quick. Let's see if this will work. Yeah. Orbitals. You guys see orbitals on here?
No.
You should.
Kind of.
You guys remember the different blocks that we talked about?
Vaguely.
Vaguely, right? So what different blocks do we have on the periodic table? We have S, P, D, and F, right? Arbitrarily chosen letters to represent arbitrary shapes, yes? No. Maybe arbitrarily chosen letters, right? So that's a good question. I don't know why. I don't know how they came up with the specific letters for that. I bet there's a reason.
Maybe they're represent them in another language.
Could be.
Because
That's probably
sigma
it.
bond, pi bond.
Well, that might be a chicken the egg argument, right? You know, what did they discover first, right? But we'll get to that too. But anyway, so if we're dealing with the different blocks on the periodic table, okay, starting on the left-hand side, get a little purple action here. There it is. Got that. We move to the middle. Nobody cares about that. No, I'm just kidding. Right? I'm not going to draw a whole box around that. I think you guys get the idea there. So we got the purple, we got the black, we got the red, we got the green there at the bottom. Okay. Okay. What's in purple?
S.
S block, right?
You forgot to put helium in purple too.
Yeah. So you'll notice that I didn't box anything around helium there. Helium technically is in the S block, although it doesn't exist there in the terms of the structure of the periodic table. Okay. So we got the S block in purple. In black we've got our
D.
D block. In red we've got our
P.
P, and then in green we have our
F.
cool. What's an S orbital?
Circle.
The sphere. Okay. What else?
Simple.
There's only 2 valence electrons in the outermost shell.
Okay.
Or it can only fit 2.
So a couple of things here that are starting to come out from Gen Chem, right? First things first, S orbitals on the left-hand side. They have a spherical shape to them. How do we know that?
Guessing.
Nope.
Electron microscope.
Nope.
Behavior.
Math.
Math. Right? Remember, we can calculate the position of an electron, right? To an extent. I'm simplifying pretty complex stuff here, right? We can't really tell where the electron is, though, right? But what can we do? We can give a probability about where we're going to find it, right? And if we graph out that probability for a 1s orbital, guess what it's going to look like?
A circle.
A sphere. Got it? It's going to look like a sphere. And that electron exists somewhere inside of there with a 90% probability. Got it? So the electron's somewhere within that probability region. That comes from Schrodinger's equations and wave functions and all this kind of stuff. Electron densities, these kind of things. Okay? You guys with me on this? You guys remember your quantum numbers? You guys remember missing those in Gen Chem? I wouldn't say I missed them, Dr. Eaton. Okay. You guys remember your quantum numbers? N and L and M sub L and M sub S.
How convincing do
You guys remember those?
Not a lot.
Some yes, some no. So you need me to help you out with it? Is that worse?
Yeah.
Okay, cool. All right. So I like feedback, okay? So when I ask you guys a question, I know it wasn't all that long ago where I was sitting down in your guys' seats, and whenever the professor asks a question, immediately your first response is, I don't want to say anything because people around me are going to think I'm a dum-dum, right? I don't want them to think I'm the only one who doesn't remember what the azimuthal quantum number is. Everyone knows what that is. I was walking down the road and they were talking about that, right? Right? So don't be, just, if you guys need a hand with something, just let me know, okay? Say, hey, do you guys remember quantum numbers? Just say no, and everyone else will be like, whew, thank goodness that brave person said it, right? Okay? So quantum numbers are what's going to help us give the, let's say, the mailing address for electrons, okay? When you give a mailing address, what do you need? The street number, right? Street name, the city, and the state, and then I ran out of, that ruins my analogy though. So, we don't need a zip code in my imaginary universe. Ah, come on, I'm not that clever. Right, you guys get what I mean? We need certain bits of information so that the letter gets to where it needs to go. You guys with me on that one? Right, so we have 4 things that we need to define where an electron is, okay? We're going to need 4 principal quantum numbers, and that's going to tell us exactly where an electron's hanging out in the periodic table around a specific element. Yeah?
4 principal numbers that tell us where an electron is.
4 quantum numbers that give us information about where the electrons are. Yeah.
Within the orbital, or?
Yeah.
Okay.
Not within the orbital, in which orbital. Remember, we can't tell exactly where it is in there, right?
Okay.
So, cool. All right. So we have our principal quantum number, N, right? We have L, we have M sub L, we have M sub S. Our principal quantum number defines our energy level. Okay, right now some of you guys are like at a 0 or a half. Okay, low energy. Ooh, tough crowd. All right. Yeah. Right. So an energy level is kind of the same thing that we're talking about here in an element. Okay, the higher the number, the higher energy it is. Got it? The lower the number, the lower energy it is. Now, what are we talking about when we're dealing with energy and orbitals and electrons and all this kind of stuff? Well, where is the low energy state for an electron? Yeah, maybe.
Isn't it by the row? The lower than the energy in an atom would be the closer it would be to either of the ends.
Either of the ends.
Sorry,
Ends of what?
with respect to this, the rows, so either on this side or this side, the lower its energy state.
Well, what I would say is that every element in here, right, let's say if we just had a magic jar that had all the different elements, they would all be at the lowest energy state, no matter where they are in the periodic table. Okay? Yeah.
So with the smaller the number, the lower the energy, is that only in terms of the principal quantum number N, or is that in terms of all of them?
Yes.
But what Joey talked about right now.
Yes.
Isn't
So
it,
hang on to that thought, right?
wouldn't it be an electron, like the lower energy state is gonna be closer to the nucleus?
Perfect. Got it? What's the low energy state for an electron? As close as it can legally or reasonably or potentially get to whatever's positive. How does chemistry work? By electrons and something negative going to something positive. The closer, right, the closer it can get to something positive, the happier it is. And it can get into the low energy state, right? Does that mean everything is going to get into the principal quantum number of 1? No, right? Because we have restrictions about how many electrons can live in certain orbitals. Got it? But if an electron can live in the 4s orbital, for instance, and we put instead into the 7s, okay? So in the 4s orbital, it's got a nice jacuzzi and sauna and everything, right? But for some other reason it wants to go live in the 7s. Is that higher energy? You bet. Is it in the ground state? No, it's not. Got it? Because it could potentially live in the 4s instead. All right? So electrons moving up and down in orbitals, Did you guys do that lab in Gen Chem where you like burn different metals and you saw different colors come out of it? That kind of, right? You guys remember that? So those are fireworks, right? That's how fireworks work, right? They put the different metals and they go make kaboom and then pretty green colors and purple, right? So you guys just made mini fireworks in the lab there, right? But those colors,
so proud.
yeah, but those colors come from, right, these electrons hopping up and down these different orbital levels. Got it? They get excited by the energy you put into it, right? And then they fall back down and they release that energy. Because everything has a tendency to go to the ground state, okay? Now, for what it's worth, and because I'm getting recorded, I have to hedge all my bets, otherwise they make mean comments, right? I'm simplifying this quite a bit, right? And if you guys get to physical chemistry, which fortunately you guys don't have to take, right? Do I have to admit this to you guys? I know that in your minds, I am the embodiment of perfection as a chemist. And so I have to pop that bubble for you guys, okay? I got a C in chemistry, in my physical chemistry class. And I was never happier than to get that C. Because the class average was a 42 at the end of the semester.
Holy
And the
crap.
professor was like, you guys are idiots, I'm not gonna curve. I was like, so anyway, a really, 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 really difficult class. And I'm glad I passed through that. Anyway, what's up?
Ground state is at the lowest energy thing it can live in.
Yeah, essentially, right? As close as you can get to the nucleus, right? That's kind of how we'll approach that. But anyway, if you guys go into PChem or like some of these other physical, you might even talk a little bit about this in biochemistry. You'll talk about things called Boltzmann distributions and where electrons actually are and all these kind of things in there. So it does get a little bit more complex with respect to that, okay? But our principal quantum number N. Now, I'm going to erase this purple thing here just to kind of make some space for us, but hopefully you guys are following with me on this. So in, let's do blue here then. So if you get your periodic table, right, you can number 1, 2, 3, 4, 5, 6, 7 along the left-hand side there, okay? Now we can use that numbering to tell us what quantum level we'll be in, what principal quantum number we'll have, okay? There's a couple of caveats with this. We'll go through it very quickly. Remember, this is in Gen Chem stuff, so I'm just kind of knocking the rust off for you guys here, okay? But here's how this works. You guys told me previously that this is the S block, okay? Right, this is the S block. So for lithium, I'm dealing with a 2s orbital. You guys with me on that? It's in the 2 there. The 2 is our principal quantum number. And it just so happens that the number on the left-hand side corresponds to the actual orbital number for lithium there. You guys with me on that one? Okay, we'll talk about where that kind of changes a little bit, so just be careful. Okay, what's up?
And that number is N, like the 2s that represents the N.
Yeah, the 2 in there represents, yeah. Okay, you guys with me on that? All right, yeah,
Wait, so N is the orbital number.
the principal quantum number.
Okay. And so 2 in front of S is the principal quantum number. Is that when you're drawing, like when you're doing 1s2, 2s2, 2p6, whatever?
Yeah.
So those numbers in front
Yep.
are quantum numbers.
Yep. Okay, now how many electrons does lithium have?
3.
3. Can all 3 of those live in the 2s orbital?
No.
No, right? So this is the other thing that we'll have to talk about, and we'll probably pick this up next time here, right? So remember, we have to take a walk through the garden, okay? To get to lithium, I have to take 3 steps. 1 step for each electron that I add in there, okay? Well, one of the important things to remember is that each orbital, no matter what it is, okay, can only hold 2 electrons. You guys with me on that? This is important. Any orbital that exists ever, even the ones that we never talked about in this class, G orbitals, H orbitals, what? Okay? Those can only hold 2 electrons. But you guys already knew this, right? Yes. But did you understand what that means? I think so, Dr. H. Right? Let me ask you a question. All right, we're going to skip ahead a little bit here, but something maybe to chew on for a bit. What's a bond?
Sharing of electrons.
Okay.
Let's go back.
Sharing of how many electrons?
Depends
Typically.
on the bond.
So 2.
2.
2. Where do those electrons in a bond live?
Between the atoms.
They're
In an
jumping-
orbital. Guess how many electrons can live in any orbital? 2. Oh. Is that just a coincidence, or is that how science works? Got it? Is it important to remember that?
Yes.
Is it important to remember that 2 electrons live in any orbital, and any orbital can hold 2 electrons? Absolutely. Okay, hang on just a second. Okay? We're going to be doing organic chemistry. And if you go back on some of these definitions that I've given you here, organic chemistry is the transformation of carbon. Got it? What does that mean for us now? In context, we're going to be doing what? Making and breaking bonds to carbon. You guys following along how I'm trying to connect this together with you guys? If I'm making and breaking bonds, how many electrons am I moving? 2. This is extremely important, okay? Because if I make a bond, I have to break a bond, okay? This is going to be one of these statements that I say to you guys over and over and over again. One of the isms, right? These little trite statements that I give you guys to remember things in 2 years. And you guys are taking the MCATs, right? You're like, oh crap, how does organic chemistry work? Make a bond, break a bond. That's a good place to start, okay? Dealing with 2 electrons, very important. Yeah.
Sorry. One thing I always get confused about with orbitals and
Yep.
how they can only hold 2 electrons is that, like, I don't know, I call it orbitals, it might be the wrong name, but when you're drawing,
Yep.
like, the circles, right, sometimes you can have up to 6 or 8 electrons on just one.
So you're talking about when you have kind of, let's say, this the picture of an atom from the solar the solar view of things, right? You have a nucleus and just electrons are floating around in these arbitrary rings that we draw there, right?
Yeah.
So that is an oversimplification of how things are, right? I would say, and I don't mean this in a negative way, I say that's an incomplete picture of what's going on. Is it useful to see that? Maybe. Does it give you an actual picture of what's going on? No, right?
So if I were to draw like 2p6,
Yeah,
right, even though it has 6 electrons, it's 3 different orbitals?
correct.
Okay.
Right? But the orbitals have a different shape, and we'll talk about that in just a minute,
Okay.
right? Yeah, so that view of like this, planets orbiting the nucleus there is not quite the same way here. What's up?
Question regarding bonds. You said an orbital holds 2 bonds an orbital holds 2 electrons and a
Yeah.
bond is made up of 2 atoms.
Yeah.
Would it theoretically be correct to say that a bond is when 2 atoms are sharing a single orbital?
Yes. Yeah.
Okay.
But we'll talk about how that's sort of true and not true. I'll talk about lies that I tell you guys face every day. How's that sound? Yeah? You guys don't even realize it.
We just expect it at this point.
You just expect-
You've
Fair
lost
enough.
all credibility.
Yeah, fair enough. Any other questions before we wrap up for the day then? All right, next time we're going to finish up talking about electrons and where they live. Okay? We're going to go on, we're going to continue talking about periodic trends, and we're going to start to get into how to draw Lewis structures. Okay?
Here's an important question.
This is just the easiest one I had.